My name's Chris. Let's do science. Chris does science. Gotta work on that intro every day. In the words of my 11-year-old daughter, today we are talking about a physics baddie. You might know this guy from Newton's law of universal gravitation or Newton's 3 laws. He is, of course, Isaac Newton. So let's look at a standard 5-mark question about Newton's model of light and how it can explain the behavior of light. Let me write it up. So here we go, stock standard 5-mark question. Tell me a little bit about Newton's model of light and tell me a little bit about a couple of things that it could be used to explain. I want to highlight to you some keywords and phrases so by the end of this video, you're getting 5 out of 5 for this question and any other similar question. First thing you should notice, 2 verbs. Describe, indicate main features, tell me a little bit about it, whereas outline is sketch in general terms. The fact that it says general terms often makes students think it's a very low level verb. It's between identify and describe or something like that. Now, one thing I learned when I was HSC marking is that outline is treated as a weak explain. So you must show cause and effect. So anytime you see explain, outline, describe how, describe why, cause and effect, that as. First part of the question, tell me a little bit about Newton's model of light. Now, some keywords and phrases I would expect a Band 6 student to include are the following. Ideally, we include all 4 of these concepts in our description of Newton's model. So it would say something along the lines of Newton's model was a corpuscular model. And then in brackets, probably something like particles of negligible mass. Really importantly, it's not zero mass. Must be negligible mass. These particles are perfectly elastic and they travel in a straight line. Cool, that's our description of Newton's model. Next step is to outline a couple of things that Newton's model is able to explain. So it's often written as, what can Newton's model explain, or what are some pieces of evidence that supports Newton's model? And these questions generally refer to the time at which Newton came up with his model. Now remember, this is the late 1600s, early 1700s. So we can't talk about any particle stuff in terms of Einstein and the photoelectric effect or even quantization. So what were some things that Newton's model could explain back at the time that it was proposed? 4 main things. Number 1, reflection. It had already been observed that when light is incident at a boundary, that the angle of incidence is equal to the angle of reflection. Newton's model could explain this in terms of corpuscles being perfectly elastic. The idea was when the corpuscles encounter the boundary, there is a force applied between the corpuscle and the boundary, and this leads to the velocity of the corpuscle flipping along the normal. Seeing as there is no force applied parallel to the boundary, that component of the corpuscle's velocity stays exactly the same. So we end up with something like the following. So if we're just looking at the magnitude of the components of the velocity vectors, this guy and this guy, exactly the same. This guy and this guy, also exactly the same magnitude, but just flipped in direction. So when it's moving towards the boundary, it's going in at a speed of v at an angle of theta. Then there is a force applied along the normal, which changes it from v cos theta into the boundary to v cos theta away from the boundary because it's perfectly elastic. Which means on the way out, it's still traveling at v, it's still moving at an angle theta. That is, angle of incidence is equal to angle of reflection. So it can explain that. What else can it explain? Firstly, you need to understand again, Snell's law was already around when Newton was coming up with his model of light. So he had to make his model fit Snell's law. There are 2 important things that we need to be able to explain in terms of refraction. Number 1, why does it travel in a straight line when it's in the bulk of the medium? So here's my corpuscle. It's in the bulk of the medium, which means all the particles in the medium, it's nice and super uniform. So the forces which my corpuscle experience are balanced. I'm going to draw in the forces acting on my corpuscle right now. The main thing is to see the force is F in every single direction, which means all the forces cancel, and therefore the corpuscle continues to move in a straight line. The corpuscle has now arrived at the boundary, and the forces are no longer equal. Because the second medium is more dense, there is a larger attractive force pulling it into medium 2, and this force is applied along the normal. Now I've greatly exaggerated this, but hopefully you see the main idea, and that is that the component of the corpuscle's velocity along the normal increases. Now how does this explain why the angle of refraction is less than the angle of incidence? Let me show you. So here are our 2 components of velocity before it strikes the boundary. This being the velocity perpendicular to the boundary, this being the velocity parallel to the boundary. And due to those velocities, we can figure out what the angle of incidence is. The corpuscle then arrives at the boundary. Remember what we said, there is a force which is applied perpendicular to the boundary. So that means this guy increases. What does that mean in terms of angle? So when the force is applied perpendicular to the boundary, the component of the corpuscle's velocity perpendicular to the boundary increases. And this results in the angle relative to that velocity vector, i.e. the angle relative to the normal, decreasing. Therefore, the angle of refraction is less than the angle of incidence. This ties in with Snell's law, but he says it bends towards the normal because it actually speeds up. So essentially it says at the boundary there is unbalanced force. This causes it to speed up into a more dense medium, and then, therefore, it bends towards the normal. This could also be used to explain why it bends away from the normal in less dense media. Ultimately, this is one of the downfalls of Newton's model when Foucault did his experiment in the 1850s to show that light actually slows down in water. So what else was Newton's model able to explain? So how was Newton's model able to explain dispersion? Remember Newton said that the corpuscles have negligible mass, not zero mass. The idea behind dispersion is that at the interface, all of the corpuscles experience the same force. However, different corpuscles actually had different masses. So he essentially says at the interface, seeing as they're all experiencing the same force, the one with the lowest mass will deflect the most. Seeing as blue deflects the most, it must be the corpuscle with the lowest mass. So that's three things that light does that Newton's model was able to explain. There is a fourth thing that's kind of a bit meh, and that is polarization. So let's talk about the whole picket fence idea of polarization, where we kind of treat it like there are fence pillars or something like that, and there's a gap between the fence pillars, indicated by my labeling this D. Now, if the corpuscle's width is less than D, the corpuscles will be able to move through. So how did Newton explain that it passes through sometimes, when I rotate the filter 90 degrees, it no longer passes through? And his idea was pretty simple, and that was that corpuscles aren't perfect spheres. He said the corpuscles have sides. So let's treat the corpuscle like a little rectangular slab. Enter Newton's corpuscle. When arranged as such, it is able to fit through the gaps. Awesome, it makes its way through. But what if the corpuscle's rotated 90 degrees? Now we see the corpuscle is actually too wide and it can't make it through the gap, so it's blocked. And this was Newton's explanation on how the corpuscular model of light could account for polarization. Corpuscles are not perfectly spherical. Corpuscles have sides. And there you have it. 4 things that Newton's model was actually able to explain. I would say you only need to remember 2 of them. The first 2 are probably the best 2 to remember, but there have been 7, 8, 9 mark questions before in trial exams about Newton and or Huygens. So if you want 9 out of 9, got to show extensive understanding, know all 4 of these. Done.